So thank you for inviting me to this workshop. So it's a great pleasure since I'm working on this topic since many years. So of course, being there for listening to the other speakers is a great opportunity. Thanks for organizing the workshop also in these difficult times. So what I will talk about in this this talk is a summary of the activities that we have been carrying on since, I would say, 10 years or so on the topics of share control. So a little bit of context. So we want to have robots working together with humans for many reasons. So we can find really a lot of reasons if you want for why this is important. But for example, there are technological limitations. So we all would like to have robots which are all capable and able to do everything on their own, but we are not there yet in many cases, as we all know. So we need the presence of human operators for helping in achieving a task in many situations which are not very well structured or predefined. Sometimes the task, so the robot needs to work together with a human because the task is such that, for example, if they have to carry an object together, or also another point which is not considered every time, but I feel is still very important, is that there are many legal issues and safety regulations that prevent the use of autonomous robots on their own, all alone, for example, in public spaces. So you need to have a human supervisor there for controlling the situation. And so we could go on in this list, but I mean, because of all these reasons, it's important to study how to best interface human with robots. And I guess everyone knows this video. So this is, I mean, now a bit old 2015 video of fails of autonomous robots. Of course, I mean, this is a collection of the bad cases, but we can get a sense of, at least in 2015, but I think that in 2020, we are not so, I mean, yeah, the situation has evolved not so much from this time. Autonomy is not able to solve everything, especially in complex situations like humanoid robotics. And we try to place ourselves so in the middle of this spectrum from, can you see the pointer of my mouse or not?
Yes.
Okay,
yes.
Okay, thanks, yeah. So from manual control, which, so an operator gives, is in direct control with the robot. So for example, in this case, I think this is an example from the nuclear industry where an operator is controlling joint by joint a manipulator in the room to a peer-to-peer. So we place ourselves in the middle. So the robot needs to have some autonomy because, of course, the operator cannot be charged with dealing, it cannot deal with everything by himself. So a human operator can control, I don't know, maybe 2, 3, 4 degrees of freedom at most. We have some joysticks on device, but then the mental loads quickly become very, very, very heavy. So the robot needs to have autonomy for dealing with all the low-level aspect of the task that cannot be handled by the human operator. But the human operator is there and is controlling part of the task via a small set of degrees of freedom of inputs. Okay? So this is a metaphor that I didn't find myself. So I picked this from a PhD student of mine, but I like it very much. So you can imagine manual control is like riding a bike. Okay? So if you want to ride a bike, you have to be fully focused on riding the bike. No? Because if you try to do something else while you ride the bike, then let's say the situation can become very, 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 very bad very soon. While if you are riding a horse, let's say horse is a kind of shared control if you want, because a horse is a semi-autonomous system. So it has it's able to keep balance, to go along a predefined direction, to avoid obstacles, but then the operator is there and gives some kind of high-level commands via the reins. Okay? So we try to do the second example, of course. So the main philosophy that we have been using in our work is to, which I think is shared by almost of us, is to design forward and backward interfaces between the operator and the robot, which can be either singular or plural. So we can address either single robot or multiple robots. So the forward interface is how to map few human commands to the many doves of the robots. And this is the part where, let's say, we engineers, we have to do some work. So how to find this mapping between maybe 2, 3 degrees of freedom and many 10, 20 degrees of freedom of the robots under control is a problem. It's one of the challenges. So this part needs some work. And then we also have the backward interface. So the robot is doing a task, and it has to inform the operator about what is going on. And so the operator typically is controlling the robot via using a device and having some feedback, for example, visual feedback and force feedback, haptic feedback. These are the typical situations. And so the robot has many constraints. It's evolving in a complex environment, so it has to send back information to the operator, but again, this information has to be compressed somehow. It cannot inform about everything because the operator would very quickly lose sight of what's going on. So this backward interface is like the inverse mapping somehow of the forward interface. It has to compress what's happening to the robot to the few channels, to the few inputs available to the human operator. So just a quick sketch. So this is a generic sketch of how we approach this kind of problems. It's generic in the sense, then in every situation, of course, this sketch will be adapted to the situation. So it has to be taken as a generic overview. So we have an input device, a master device. In general, we use force feedback devices. So we model the device as a typical second-order mechanical system with control torques and the human input forces. And then the robot is a nonlinear system. So whatever, it's a generic nonlinear system. In this case, I modeled it as a first-order system, but you will also imagine it as a second-order system or more complex system. So the robot has some inputs, U, and these inputs are divided into a human command and an autonomous command, with some orthogonality properties among these two components. So we would like to have the human commands orthogonal to the autonomous commands according to some metric. Now, in this example, the metric is just the Euclidean metric, but you can imagine using any kind of metric of interest. And this orthogonality is important because in general, we don't want to have the human commands interfering with autonomy and vice versa. Then, and a hard part in general in solving this kind of problems is to encode. So the robot has many constraints, many requirements. For example, the joint limits, singularities, obstacle avoidance, and requirements such as reaching a task, keeping balance, and so forth. So all these kind of constraints requirements in this kind of way of approaching this problem need to eventually become encoded into some kind of cost function. Now, this cost function in this plot is very simple, but in practice, this cost function can be arbitrarily complex. So a lot of work, a lot of engineering work goes into the design of this cost function, which can be very complex because the constraints or the requirements can be very complex. Then once we have the cost function, another step that we engineers have to do is to design the forward interface. So how to map the few degrees of freedom on the haptic device, on the master device, to the human commands. And this mapping is done via this matrix QF, which is in general a rectangular high matrix. So few human commands xm or x.m, depending on whether the human is controlling in position or velocity, and many robot commands UH. Then once this is chosen, the autonomy, basically what the autonomy tries to do is to minimize the cost function H in the null space of this mapping. So this is the orthogonality property that I was talking about before. So the autonomy tries to do what it can for minimizing H while not interfering with what the human is commanding. Okay? And then for the backward interface, basically the autonomy is optimizing H in the null space of the forward interface. And then there is one part left, of course, from this projection, the part which would be in the space of the forward interface, which is this part. This is basically how the autonomy would like to move the human commands for optimizing H. And this is given back as a force Q to the human operator. Again, in this way, if the operator is controlling in velocity, or in this way, it's a spring if the operator is controlling in position. Okay? So this is a general sketch, again, of how we approach this kind of problems. Then we use these ideas in many different contexts: flying robots, singular multiples, and telemanipulation. So this is just a collection of some, by now, old videos about early works on this topic. So In this case, an operator via an haptic device was controlling a group of robots that needed to keep a formation, a geometric formation, while avoiding obstacles. And the operator was commanding the velocity of the center of the barycenter of the formation, and it was receiving a force which was basically representative of the repulsive action of the obstacle. In this case, the operator was controlling one leader robot, this one, while the other robots were following the leader robot via virtual spring-like couplings. And the operator was feeling basically a force proportional to the difference, the mismatch between the commanded velocity and the actual velocity of the leader. And the leader could have a velocity different from the commanded one because, for example, it could be dragged by the other robots which are following, or it could feel presence of the obstacles, so the repulsive action of the obstacles. This could also be, we will also complexify this idea by encoding more complex constraints. So in this case, the situation is quite similar, but there is an additional constraint, which is a much more complicated constraint, if you want, that the group needs to keep connectivity of the graph at all times. So the graph can never become disconnected. So if the operator tries to move the leader in a direction, like in this case, where the graph would become disconnected, then the force feedback is informing him that this is not a good direction to move, and he should wait while the other robots reconfigure for not disconnecting the group. And finally, we also use another approach that I like a lot, which is basically a trajectory-based shared control, if you want. So what happens in this case is that the operator is not controlling the instantaneous velocity of the robot, but the robot needs to follow a trajectory. So for some reasons, because of the task, the robot needs to, for example, cover an area and it has to follow a trajectory. And the operator can control some properties of this trajectory. In this case, for example, it can control the position of the barycenter, the planar orientation, and the expansion of the trajectory. And there are some constraints, obstacles. For example, in this case, the robot needs to avoid obstacles. And the trajectory is modified by the robot, but ahead of time. So if there is an obstacle that could be hit, I don't know, in 5 seconds, the trajectory is autonomously modified by the robot in order to avoid the obstacle in 5 seconds. The nice point is that the operator receives a feedback, a force feedback, which is informative of what will happen in the future. So to explain it easily, if the operator tries to move the barycenter to the right, and moving to the right means that in 5 seconds the robot will hit an obstacle, then the force feedback tells the operator don't move to the right, because otherwise in 5 seconds the obstacle will be hit, and maybe it's better to move the path, I don't know, to the front or in another direction. So it's a kind of predictive force feedback, if you want, that informs about what will happen in the near future. And I think this approach has a lot of potential, especially for complex situations. So now, coming to more recent work, we worked a lot in the context of a European project, Romance, in TeleManipulation for sort and segregation of nuclear waste. So the idea is that so sorting of nuclear waste is done mostly manually, in the sense an operator is manually controlling a robot for taking the waste and sorting it and manipulating it. And of course, one would like to automatize all this process. But automatizing is not so easy. So we in the sense, because the handling waste can be quite tricky. So we would like, so people in the industry would like to have human operators in the loop, especially expert operators who can steer, who can control at high level these the manipulators. So what we did in this context is to consider this kind of setup, which is representative of the setup which is really used in the, was really used by the industrial partner we had in the project. So one manipulator is a gripper for manipulating, and another manipulator is there with a camera on board for looking at the gripper and at the object. And this information is needed for estimating the relative pose between the gripper and the object. And then this relative pose is needed by the algorithm for approaching the object and for manipulating. Okay? So an operator cannot control, at least let's say a standard operator, cannot control 2 manipulators at the same time, joint by joint. Of course, it's impossible. In this case, it would have to control 12 degrees of freedom. So we need to design some interfaces for letting the operator to control easily this system, this 2-arm system, and also providing, again, a force feedback informative of what's happening to this complex system. system made of 2 arms. There are joint limits of both arms, singularities of both arms, and you can complexify the situation as you want. Yeah? So we addressed, let's say, the 3 phases of the manipulation action. So approaching the object, grasping, and then doing a post-grasp manipulation action. So now just to give an example, so some concrete examples of what we did. For example, in this case, one of the first attempts was to say, let's imagine that the gripper needs to approach the object, but it is constrained so as to always look at the object. So in general, you want to approach the object while looking at the object by having the gripper main direction aligned with the direction going towards the object for grasping. Then this constrains 2 degrees of freedom for the gripper. There are 4 degrees of freedom left, and these 4 degrees of freedom are controlled by the operator, but along an interface, which means basically along some predefined geometric primitives. So in practice, we say the operator can command the robot along these 4 degrees of freedom by moving over a sphere centered at the object, by approaching along the connecting line, or by rotating about the connecting line. So this, in our opinion, could give easily understandable interface for an operator which is already expert in this kind of tasks. Yeah? And the other robot, the robot with a camera, needs to move autonomously, always so as to always keep in the field of view the gripper and the object. And the 4 cues, which are here at the bottom, are designed so as to, sorry, I forgot, we have system constraints as always, which are encoded in the cost function. And in this case, the constraints were joint limits and singularities of both manipulators. So of the manipulator with the gripper and the manipulator with the camera. And the 4 cues were designed so as to inform the operator how to move, but only along the 4 directions which are given to the operator. So the approaching, the moving along the sphere, and rotating. How to move so as to minimize the cost function. So the system tells the operator how we should move along this interface for staying away from the constraints. And the autonomy takes care of the rest. So this is an example of the implementation. So this is the camera view where the robot with the camera is moving so as to keep the gripper and the object in the field of view. The operator is activating this interface for approaching the object or moving along a sphere while approaching the object for grasping. And you cannot see it in the video, but it's also receiving 4 cues for informing about the proximity of the constraints. And we, in the context of the project, we did an implementation also with a nuclear certified arm at CA for showing that this technology could be ported, of course, also to this kind of arms. So then another extension that we did, this was along the lines of the trajectory-based shared control that I talked before in the context of the mobile robot. We said maybe the operator, instead of just controlling the instantaneous velocity right now, it could be interested in controlling, so imagining that there is a trajectory that is defined by some algorithm that defines how the gripper and the camera should move for approaching the object. The operator may be interested in controlling not the instantaneous velocity right now, but some properties of the trajectory ahead of time. For example, the final pose. The gripper may be here, there is a trajectory that goes down to the object. The operator may just want to move the final pose of the trajectory, while the rest of the trajectory from here to the final pose is optimized by the autonomy. And the same for the camera. The camera has also a trajectory that will tell the camera how to move while the gripper is approaching the object for keeping everything in the field of view. And also the camera trajectory is optimized by the autonomy. So without entering the details, which are a bit, let's say, convoluted, we define trajectories in terms of a parametric polynomial, in particular B-splines. And the operator was given access to some degrees of freedom on the final pose of the gripper, and both trajectories were optimized at the same time. And in this case, we could also include not so trivial, let's say, visual constraint that was imposing the camera to always move so as to keep the gripper and the object in the field of view, and also not occluding themselves. So by modeling the gripper and the object as spheres, we could include the constraint of having, not having an occlusion between the gripper and the object while the camera was moving. And the operator was, again, receiving a force feedback informing about how to move the final pose of the trajectory so as to keep the both trajectories far from the constraints during motion at all times. All right, so since I guess I'm running late, I will try to go fast on this part. So then another extension that we did, and again, this is an idea that I find it quite interesting, is to address the post-grasp manipulation action. So the idea is quite simple. Imagine that you manage to grasp an object. Now, in general, you grasp because you want to do something. You don't grasp just for the sake of grasping. You grasp because then you want to do some action. You want to move the object from here to there, for example. So imagine that the manipulator grasps an object, and then the trajectory that the object needs to follow after the grasp is given. So the object needs to go from here to there on the shelf, for example. So one degree of freedom which is left to be optimized, to be taken into account, is the grasp pose. So you may grasp the object like this. So I don't know if I have an object here. I have my phone. So you can grasp it like this, or like this. But this grasp location makes a difference for then executing the post-grasp action. If I grasp the phone like here, like this, then it's easy to move it like that. But if I grasp it like this, then it's kind of harder to move it like this. Yeah? So what we did was to, let's say, implement this idea into a shared control scenario. So the idea is that the operator has a good way of judging if this or this or this is a good grasp because of its experience. But the operator has a hard way of judging whether this grasp or this grasp or this grasp will lead to a good action for the robot. Because, for example, by grasping the object like this, the robot could not hit a joint limit while moving along the trajectory, while grasping the object like this, the robot could hit a joint limit, for example. And of course, this is impossible to be judged in general, I would say, by any operator. So we blended these ideas, and what we did was to define some metric for judging whether a grasp is a good grasp. So the metric is basically, apart from the details, at the end of the day, is the integral of the projection of the manipulability ellipsoid of the manipulator along the trajectory. Yeah? So basically what we did is we evaluate by grasp, if the robot grasps the object like this, then the manipulability ellipsoid that will result from this grasp along the trajectory will, the integral of this ellipsoid will give some result, and will give some metric, will give a number, an answer. And then this metric is what we want to maximize. We want to max the projection of along the path of the manipulability of ellipsoid. It's just a possible metric, of course. So you can imagine any other metric of interest. And then once we have these metrics, the integral of this projection along the path, the free variable which is left is where to grasp. Here, or there. So the grasp pose. And then the force cues can be built from the gradient of this cost function with respect to the grasp pose. So the force cues will tell the operator where to move, such that the resulting grasping pose will be good for the manipulative action. And this idea can be, again, complexified at will. For example, you are now preparing an extension that also includes the dynamics of the robot. So it's not only about kinematics, about manipulability, but it also includes the torque capabilities of the manipulator arm for torque control robots, for taking into account the inertial mass of the object to be moved. And as an example, so if the operator was told to grasp this object, he will grasp this object probably like this, for then moving it along the red line. But it turns out that grasping the object like this, it's bad for the robot, because by grasping the object like this and then moving the object along this trajectory, the robot passes very close to a singularity. While this is the best grasp for avoiding the singularity. And again, the decision on what grasp to use, to choose, is left to the operator. The operator decides, but is informed about which grasps are better or not for the action, for the manipulative action. Then some other extension. For example, in this case, we explored the learning for encoding expert demonstration. So it's a simple idea, but quite effective, I think. So you can imagine that you can have experts demonstrating many trials, many trajectories for approaching an object. And then you have a novice user and the novice user needs to do the task. So one way to use learning in this context, at least the way that we thought it was a good way, is to take the distribution generated by the expert operator. Then this distribution will have a mean and a variance along the trajectory. So where the variance is small, this means that all the demonstrations of the expert operator were passing basically close to the mean. And this means that the force Qs then needs to be strong in this case, because the novice operator needs to do what the expert operator did, since the variance was small. When the variance is large, from the demonstrations of the expert operator, this means that basically the operator didn't care, if you want, about where the robot was to some extent. And then this translates into the fact that the force Qs can be set to small force Qs for guiding the novice operator, because the novice operator has more freedom to choose where to be. Yeah? And this idea, it's a simple idea again, but the results were quite nice. And I think it's a promising idea. In general, of course, I mean, as many of us are already doing, learning with shared control is a good direction, in my opinion, where to go next. Then another extension that we did was to embed the grasping planner into the picture. So if you want to grasp an object, you can rely on the human operator, but you can also exploit, of course, many of the existing grasping planners available out there that are able to generate feasible grasps. And this can be used as a baseline for giving cues to the operator where to grasp. So the operator judges by himself, but is aided, is helped by the grasping poses generated by the grasping planner. And we addressed cutting. Also, cutting is a nice problem because it involves some kind of non-nomic constraints, if you want. So when you cut, you cannot move sideways, a little bit like if you are considering a car or a unicycle. You may turn on the spot in some cases, or in other cases you cannot turn on the spot. You can just turn while moving like a car. Yeah? So it's a nice problem. It's a nice control problem for people from control. And we did some, without entering in details, we embedded basically presence of these non-nomic constraints, depending on whether you want to consider unicycle-like constraints or car-like constraints into the shared control for guiding the user, for assisting the user. And we also considered together, by the way, with Mario Selvaggio, one of the organizers of the workshop, we also consider, for example, the case of having two manipulators, one of which is autonomously performing a task, in this case, a vision task. So this manipulator with the camera needs to look at an object, while the other manipulator controlled by the operator has to grasp an object, and they have to share the workspace. So there is an issue of avoiding collisions within the manipulators. And also in this case, we by following basically the same guidelines of before, one could exploit redundancy for avoiding the collision. And when this is not possible, force cues can inform the operator how to move for avoiding the collisions. And yes, last but not least, one of the PhD students under my supervision, who was also one of the main authors of these works, implemented this kind of ideas also on the Toro robot during a visit at DLR. And the idea here was that so the robot needs to keep balance, and the operator is controlling one of the ends for reaching a point in space, and the rest, the autonomy takes care of the balance, and for example uses the other end and the rest of the body for keeping balance. And the force cues are telling the operator where to move the hands, is controlling for keeping balance in case this is not possible or not easily achieved by the autonomy. And yes, we did also a demonstration, live demonstration at the Megafair in Rome in 2018. That's always a nice experience because, of course, as we all know, doing a demonstration in a lab is let's say one story, but doing a demonstration in a public space with general public, it's a kind of different experience. You get a lot of questions that you would not expect, but the feedback we got was nice. It was a good feedback about part of the work that I presented. So I conclude my talk, and at the bottom a partial list of all the people involved in this in the works that I talked about. And of course, I summarized this work, but in most cases, I will say I was not the one, let's say, mainly involved in the work. Maybe I was more supervising students and so forth. So these people are really the guys who did the work. And I mean, concluding, of course, we will need shared control in the future. I cannot see anything different from this. Autonomy will improve, but the human will have to be there for many reasons. Not just because autonomy is not able to solve the task, but also for safety, responsibility reasons. And we have to advance in this field. And in my opinion, there are many advancements to be done on the algorithmic point of view, if you want, on the control algorithmic point of view. But I think a blending with learning is needed, because for encoding the human intentions, for encoding a human who will solve a problem, we have to use statistical learning, I think, and then blending with control, of course. So this is the direction that I'm trying to work on now, and yeah, I think it's a promising direction for the future. Thank you very much for listening to me, and if you have any question, of course, I'm happy to answer.
Thank you, Paolo. We have a question from Slack from Emma David, the University of Southern Denmark. So the question is, how the network overhead between the agents is considered in the system design of the decentralized shared control system?
Sorry, can you repeat the question?
So in the system design of the decentralized shared control system, how the network overhead between the agents is considered?
Okay, I say it's about the initial videos on the multi-robots.
Yeah, it was an early question.
Yes. So the network, so what we did was the laws that were guiding the robots were decentralized in the sense of having so constant complexity per agent and so forth. So then about the network load, let's say we didn't consider this point in the demonstrations because for the experiments we were running everything on a local network. So of course in lab conditions, if you want. So of course this was easing a lot the implementation. Everything was running on the same local network, and the network issues were not there basically. So if you had to consider this in a real outdoor condition, then network load will be an issue, of course. And yeah, I don't have a good answer to this point about that. It will be an issue. And having a decentralized design helps because you can limit the amount of data that is exchanged. But the controllers that we design, the controllers that would have to be modified for sure, because you cannot imagine having almost continuous communication between the robots as we were imagining in the lab. And yeah, I think it's a research direction. I don't have a good answer to this point other than it's a good question, and thank you for the question.
Okay.